Okay, let's start. Good morning, everyone. Thank you for joining this session. My name is Lilian Paiva. I'm responsible for all the life science research solutions in Latin America, together with Maria José Dávila as customer consultant. In the name of the whole team here, I'd like to thank you all for joining this session today. The purpose of the session is to officially launch, introduce, and discuss recent developments in predictive retrosynthesis and the module Reaxys RT, a new feature that will be integrated to the Reaxys platform very soon. Before we start, I'd like to share some important messages with all of you. This webinar is going to be recorded, so it's going to be available on demand for all of you and also going to be posted in our YouTube channel. All of your microphones are disabled, but you can send your question through the Q&A, and it can be in any language. If you feel more comfortable to send it in Portuguese or Spanish, you can send it anytime. And the chat is also available for you to send a special request that we're going to do. I'm going to share the agenda of the day. So just a second. Here. So this is the agenda of the day. Then we are going to have the pleasure to count with 3 different speakers for the agenda. So starting is going to be Jürgen Swente-Busch, Director Product Management Chemistry at Elsevier. He's going to talk about science behind A&E powered predictive retrosynthesis. Then we are going to have Mander Bottas, Customer Consultant Life Science Solutions at Elsevier. He's going to demonstrate Elsevier Reaxys predictive retrosynthesis. Then we'll have, just a second, Abhinav Kumar, Head of Strategy and Business Development, Reaxys Chemistry Solutions at Elsevier. He's going to do a sneak preview of upcoming developments for Reaxys predictive retrosynthesis. And then at the end, we will have time with Jürgen to discuss benefits, limitations of technology, and future roadmap. We also want to ask you, if you want us to use your molecule as an example, you can send it to us. Please post the SMILE string of the molecule into the chat, or so we can use it as example. But you have just 15 minutes to do this. So if you have any problem to post it or to send via the chat, you can also send by email. I'm going to put my email on the chat. Okay, so let's start with Jürgen. I'm going to stop sharing my screen just a second.
Okay. Yes, thank you very much for the nice introduction and also a very warm welcome to this webinar from my side. I'm afraid that I need to stop my video now so that I save some bandwidth and then I start sharing. So give me a second. So here we go. And then you should see my screen right now. Can you confirm?
Yes, we can see your screen.
Very well. Okay, well, I'm glad for the opportunity to present to you the Reaxys view of predictive retrosynthesis together with my colleagues. And in this webinar, you will learn how it works and how we will integrate it into Reaxys. And I definitely hope that you will find it interesting. All right, let's go then. So, chemistry research, as you can see on this slide, is very much about designing and synthesizing new compounds which have certain desired features. And the range of this is definitely immense. Well, to whom do I say that? It could be like in pharma, that is shown here on the screen, finding compounds that block certain biological targets, or in chemical industry, for example, finding new compound that protects surfaces from being damaged by UV radiation. The research then is very much about answering questions like what to make, and then immediately afterwards, how to make it. And especially the latter can break out a development cycle significantly. One of the contributing factors for the long time, especially in pharma, let's say the time it takes for drugs to reach patients, is that it involves synthesis of large number of drug candidates that could target a disease like lung cancer, for example. And synthesis planning and execution can actually take up to 4 to 6 weeks per drug candidate. This is definitely a long time. And while it is already optimized as much as possible, more radical and innovative step changes are needed in synthesis to accelerate the process. So the question then arises, can a data-driven artificial intelligence approach actually help to improve the situation? And in fact, we very much believe so. And that's what we will walk you through today. Let's start with how you synthesize a yet unknown molecule today. I don't know how you do it, but we typically recommend to start with Reaxys. And Reaxys is one of the biggest knowledge bases of synthesis research containing data of the last 200 years. This is really immense. However, it doesn't help if you are not really trained to work with the tool properly. Simply entering the desired molecule and hoping that the system will give you the answer right away will typically not work. But if you know how to use Reaxys properly, then it is a fantastic tool to provide help in finding proper synthesis routes for unknown molecules already. And this is proven by thousands of chemists who use it every day. So indeed, Reaxys can help already today, yet it takes time and training. So in basis, you can compare it to a sort of a street map or atlas. Everything is there, but you need to find your way on your own. But we have some good news, and that is going to change. So wouldn't it be nice if this could be changed in a way that Reaxys could provide you with suggestions that allow you to focus on chemistry and not on how to search a large knowledge base, knowing all the tips and tricks that you need to find the molecules around there, doing similarity searches or substructure searches or break molecules down here and there, and allowing you to make decisions faster and spend more time at the bench and get more molecules created. Well, this is basically what we are talking about here. It is about an idea generator that can accelerate the synthesis process, or in other words, as it is shown here, it is more or less moving from a street map into a GPS. Okay, so let's start then. In fact, the idea is not really that new. Corey and other researchers have been trying to use computing power to plan organic chemical synthesis since the 1960s, like late 1960s, but only with some limited success, we have to say. And we all know that. I mean, we are not using it right now, at least not many of us, because it did not really materialize. The tools at that time were sort of great for humans, but not so much for machines. And that is due to two fundamental problems which have frustrated the dream. First, the computing hardware simply could not tackle the scale of the challenge. And it is really a huge challenge. And the second is actually a bit more severe. It is providing the machine with an exhaustively human-curated list of the reactions that can enable a desired chemical transformation. And that sort of worked 6 years ago when Corey was doing it, but this approach is hampered by the exponential rise of chemical knowledge happened over the last 2 decades. So manually writing down the rules of chemistry is very laborious and a very time-consuming job, and it's really hard to keep up with the current knowledge. Now, That is where it actually starts. So over the last couple of years, processes have been invented and established that are able to take the content of a large database like Reaxys and extract, transform, and load it into machine learning processes to create models which can provide good answers and help with all sort of chemistry-related research challenges, where retrosynthesis is actually only one of many, just as a side note. A critical part of the process is getting high quality and unified data that is machine learning ready. The good news is that Reaxys actually fulfills most of the requirements today. So it's not wondering that we use Reaxys data as a starting point. So let's see how it works in our case then. Reaxys teamed up with a company called Pendign.AI, which is an Australian startup led by Professor Mark Waller, who published a groundbreaking paper together with Marvin Ziegler in Nature in 2018. And the outcome of this paper is a tool that we want to focus on today. In a nutshell, his algorithm is based on the following process. You take a published reaction as it comes in Reaxys. You see we have structures for starting materials. We have conditions like catalyst and reagents and solvents and temperature and time, and you get a product. And from here, you do some reaction cleaning and some standardization. So you translate the structures into smile strings, you enrich it with some metadata, like for example, ECFP4 fingerprints. Then you do some Reaxys deduplication, depending on how you have modified the reactions. And then you remove non-participating molecules like solvents, catalysts, etc. And actually, this is also one of the challenges we have to solve in the future. So in the current version of the RT tool, reaction conditions are not considered. So this is what you need to keep in mind. And then in a subsequent step, you try to map the atoms of the reactants on the atoms of the product. This is a key step of the whole process, since it identifies the reaction centers and reaction transition states, more or less. And from here, you then derive templates which are used to train the model at the end. So this is where the knowledge comes from. Well, and then once you have done this, then you get a tool which is able to solve retrosynthetic problems in a very fast way. Mark calls his approach 3N-MCTS, which stands for 3 neural networks or 3 models, which are combined with a Monte Carlo tree search. And in combination, this is able to answer retrosynthetic questions fast and scientifically sound. So it starts here, if you look at the schema, with a molecule where the tool tries to identify the most probable disconnections based on the learnings from using Reaxys dataset as a source. So in this example, you see several colored circles, which should represent possible reaction centers and starting breakpoints. So let's focus on the one which is marked as Rx, and where you want to break the bond between the CO group and the NH group. Based on this, the path would then lead to the creation of some precursors or promising candidates in step number 2. So here we have 3 candidates which could possibly react with each other to build the final target product. Now you need to decide which one is the best moving forwards, because some are still unlikely to happen based on the learnings that you have derived from the Reaxys base. And this is more or less explained here in step number 3, which is a sort of a feasibility assessment, and hence a key step in this process, since it eliminates unwanted and unlike reactions from a long list of possible candidates. So this is an ideal case, so there's more than 3 to check, obviously. But basically it checks the predicted reactions against an in-scope filter, which is trained on positive published data, but equally important, also taking calculated negative data into account. And just to ensure, so normally negative data is not published, and Reaxys therefore cannot contain them. Ideally, you would have experimental negative data at hand that can be used, but in this case, we had to calculate it, and we use the published data as a source. So there is a sort of bias in there with this approach. But since the model creation is actually very fast, we could easily use your data or other customers' own data to retrain the model quickly. And in fact, we are talking to customers today already to check whether they would like us to use their ELN data that may contain negative reactions and hence make the model more precise and successful. And this is definitely something we will follow up with our customers later this year. So finally, it comes up with the candidates to investigate further. And in step number 4, it applies some stopping criteria for any selected starting material. So we have now here 2 starting materials. And the question that the tool asks now is it already good enough to start with it? So are all starting materials readily available as building blocks? Or do I need to go down further? I should note here that these building blocks do not necessarily be commercially available. It can also be an in-house available substance, and the tool is able to handle this kind of substance libraries, and it can be loaded easily into the tool, which we have done with a few customers already. Well, if the starting material is available, then just stop right here. If not, then you need to make the other starting material as well. And then it starts from step number 2 and 3, 1, 2, and 3 again. And it does this until it found synthesis paths that start with available compounds for all branches, or a given time budget is exhausted. And once that is done, the result will be presented to the user. Well, in a nutshell, it looks like this. So it combines the Reaxys reaction knowledge base and the 3N MCTS technology from Pendign.AI to create, we call it an outstanding retrosynthesis application. You should give it a try to really see that it is an outstanding application. So we are using 15 million single-step reactions of small organic molecules. And therefore, from this, we derive roughly 400,000 reaction routes. We create 3 models out of that, and they are bound together into an application, also implementing a Monte Carlo tree search in there. And then it will come with an easy-to-use user interface showing you the results of a retrosynthesis process. Well, so far for my part of the presentation, and Mandar and Abhinav will now show you how it works in practice. So with this, I will stop sharing and hand it over to Mandar.
Hi, Lillian, can you confirm if you are able to see my screen?
Yes, I can see it. Yes, in demonstration mode. Okay.
Perfect. Yeah. So whatever Jürgen has presented today, the science behind how we have developed this tool, I will take you in the next 15 to 20 minutes through the tool live, as well as I will show a couple of examples of the tool. A couple of examples which the tool has come up with the synthetic routes. This particular, if you are able to see my screen right now, these are the 4 molecules which we have provided you in the abstract, and I hope that you have gone through this molecule and may have thought about the synthesis of this, or how you can approach this molecules to come up with the synthesis of this molecule. If not, also we will certainly show you in the live demo what kind of synthetic routes the tool has been able to predict. The syntheses are quite robust in nature. If you see that, And the tool will also provide you with the starting materials which are commercially available, right? So before going into the details of the other two molecules, I will just switch my screen and take you through the live demo itself there. So just a minute. Right. I hope you are able to see my screen. So if you see on the top, this is the URL right now, which is demo.retrosynthesis.reaxys.com. And right now the tool is in isolation, but after I finish my demo, Abhinav will take you through the integration of this tool, which is upcoming by end of June or first week of July there. So this tool is going to get integrated into Reaxys itself, so you do not have to log in the isolation. If you hit this retrosynthesis URL, then you will have end up in this landing page there. You will see here my synthesis projects, and as I have done many synthesis projects here, everything gets stored for your review. If you wish to review all the molecules you have ran through there, you can draw a target molecule there as a smile string there. So if you click here on the draw target substance, it will take you through the drawing page there. So this is a Marvin.js tool. And if you have a smile string, if you had a share, we'd have certainly shown you live how quickly this tool provides you with the solution of the predicted route. So you can just click here and then select the smiles notations, and then you can paste the molecule here directly there. So this is one of the ways to come up with the structures. If you see on the right-hand side panel, there are 4 different parameters you can choose through or play around with. So first is the length and depth of the synthesis plan. So the tool provides you with 2 options in the length and depth of synthesis plan. First is the full synthesis plan, which is 20 synthetic routes at a time is in default mode. But if you wish to go with the 100 routes, you can still choose with that option as well. And then there is an option with the last step there. So this particular option is quite useful in a way that if the tool is not able to provide you the synthetic routes of the molecules of your choice, and there are no results for that, then you can go a step-by-step approach backwards for the retrosynthesis there using this last step option. And then tool will come up with a particular intermediate where you can actually have a full synthetic route to reach out to this intermediate and then finish your synthesis there. So that is one of the options which are available there. If you see the second option here, there is a diversity of synthesis plans option as a parameter there. So what you see here is in the default mode settings, there is 3 and 3, which is reaction steps to occur, which is 3 times, and building blocks to occur, which is 3 times. So what it suggests is that if the route has provided you with more than 5 or 6 synthetic routes as options there, then the reaction step might be repeated in 3 out of that 5 or 6 routes which it has shown. And also the building blocks, it will come up it will get repeated in the 3 different routes there. So that is the default setting there, but a user can choose his own diversity. Either he can choose highest diversity or the lowest diversity. Lowest diversity is with the higher number. That means that the reaction step will get repeated as many times as you have selected the number there. Or if you choose select 1 and 1 as option, which is for the reaction step to occur only 1 time and the building block to occur only 1 time, then this is the maximum diversity option there. This allows, this is actually a post hoc filter. So it doesn't matter if you selected 3 or 1 at the time. The synthetic route will come up with its own synthetic predictions of multiple routes, and based on the diversity, once it has predicted the routes based on the diversity you have chosen up, it will then apply this post hoc filter and provide you with those specific routes where the options you have chosen will get executed. Another parameter to choose is the processing time. So if you see, you can play around with the sidebar here. So by default, it has 10-minute setting there for processing time there. And what we have seen or observed is that most of the time, the predictions actually appear within less than 5 to 7 minutes of time. Then another parameter to play around with is the building block libraries. There is also an option of custom building blocks. So if you wish to integrate your own intermediates or in-house compounds which you have prepared and want to use them as a building blocks or starting materials, then we have that option to create custom building blocks as well based on your choices. But apart from that, we also have provided you with these options here. So first option is the default standard lab chemicals there. And then the second option is Reaxys common substrates. So this data has been built on Reaxys, and hence if you see there are, as Jürgen has mentioned clearly about the data build up based on 15 million single step organic reactions. So the intermediates or the starting products or the building blocks have been chosen from there, which are labeled as Reaxys common substrates. Then we have other commercial suppliers such as Sigma Aldrich, lab networks, and e-molecules. But the interesting part, what we have given the user to choose or provide him in the power to have these options are the building blocks which are under $500 per gram or building blocks which are $200 per gram. This option is very much useful when someone wants to have a synthetic route which is predicted from this tool with overall having a lower cost. So if you choose your starting materials with a lower cost availability or the building blocks with a lower cost, then overall synthesis cost also goes down. So this option actually helps you to come up with that. You can select uncheck or check this based on your wish there. And then the final one is the building blocks from tier 1 supplier. So if you are in a hurry and if you want to start the synthesis as quickly as possible, then the building blocks from tier 1 supplier will help you to reach that particular chemical in your lab within less than a week's time. So you can choose that particular option directly and you can run the synthesis plans. So right now, I will just take you through the 4 molecules which we have provided you in the abstract. And I hope you find them interesting. So I will just show you the results. So if I click on the view results page, you will end up seeing, as this is a molecule little bit of complex nature, you see the synthetic retrosynthesis predictor has predicted synthetic route with number of steps 9. And you see also here the confidence score there. And for another molecules, you will also see if there are multiple routes, this gets rank order based on the root confidence score there, and the one being the highest number. On this part, you see the building blocks, which are again the commercial level starting materials, and you can view your route with 2 options, either table view, which is more of a reaction view, or tree view, which is a retrosynthesis view. So if I click on the tree view here, you can see the route which is predicted. And I have ran this just to again reiterate the fact that I have ran this molecules ahead of time so that I can show you directly here. So if you see here, there are various colored boxes with the intermediates there. So whichever the colored boxes with orange box or the green box are the one which are commercially available starting materials there. So if you click there, you see here the source, which is e-molecules, Sigma Aldrich, tier 1 suppliers, $200 per gram or $500 per gram. So there are multiple options there. And if you click here, you also see those kind of options where you can procure the starting material from, right? And then this takes you upwards from bottom to top till you have reached the target molecule, which was we have drawn for the prediction there. For every step, you have a link to Reaxys. So if you click here on any number there, it takes you through show Reaxys examples, and you can directly go and see the related examples of Reaxys. Before going to there, I will show you the option of the table view as well. So whichever way you like to see, one can actually click on the views which they are comfortable with. and they can view this. I personally like this view because then I am able to see that as a reaction mode rather than the retrosynthesis mode. And if you see here, when I click there, you can download those as the whole scheme as a PDF there. You can export them, you can print them or directly save it on your desktop. So if you see on the step 1, this is the benzimidazole formation there. So you start with the quinoline with a nitro and a hydroxy group. And then this diethio you actually use as a catalyst there to have this reaction going to form the benzimidazole there. And if you click on the show Reaxys examples, which I will take you through there, you will have those ring formation coming in. So as they, instead of the hydroxy group, if they have used the acid group here, so there is one more carbon there. You see the 6-member ring formation here. But we certainly will be having another examples. If you see here, the 5-member ring, which is benzimidazole formation. So it's the same compound. So you have that ring formation there. And if you want to see the examples directly, you can click the Reaxys. It will take you through the synthesis. The experimental procedures of the similar reactions, where you can actually either get the experimental procedures directly or click the link to the actual article. There is the issue. I will just click again. Sorry. I'm not able to. Yeah, perfect. Yeah. So let's click the link again. Yes, if you see here, we have the reaction conditions there, and there is a link to the actual article there. One can go and download the reaction. So in a way, there are 25 options, which is rank order again with the similarity of the molecule. If you see here on the top, we have the reaction similarity score there. So even though the scores are lower, because as Jürgen has presented in his part of the presentation, he has shown the atom mapping there. So this atom gets mapped with the original. If you see here, our originals have the benzylamine there, but and then we have this nitrophenol, quinoline nitrophenol there. So as these molecules or this building blocks are not the same as what we have in our predicted route, the reaction similarity scores goes down based on the atom mapping. But you will certainly have the closest similarity you can if you see those options there. And as we found, even though the reaction similarity score was less than 0.5, we found about the benzimidazole predictions there. So this is how it takes you there. I will take you to the another route where we have more routes predicted by the predictive retrosynthesis. There is one question asked by Alfredo that there is always be an answer for a given molecule, or is it possible to have 0 hits? So it is possible to have 0 hits. And as I shown you during the structure drawing tool, that when we get, or when a user gets 0 hit, he can use the last step options as well to come up with the step-by-step approach of the predictive retrosynthesis there as well. So if you see here, the tool has provided 3 different routes, and the number of steps have been given, and you have the root confidence store of that. So I'll take you through one of them. So as I said, I like the table view approach. I will take you to the table view of this particular synthetic molecule. Again, this is one of the molecule which we have actually captured in the abstract. So this particular prediction actually arrives at a very viable synthetic route in less than 10 minutes, as I showed. As you have seen, it provides you the logical flow with proper disconnections with decreasing complexity. It takes into account the protection deprotection as well. And if you see on this particular synthetic route, you start with the 5-bromo isoquinolinone, and you have the bocahydrazine which gets reacted there to form the bromo gets displaced for the preparation of the Bock hydrazine there. And once it gets at form, then you deproduct the Bock. So it certainly undergoes the deproduction strategies here, which I was able to show you there. It gets down to the commercial level starting material. So as I have shown you, it also shows you the commercial level starting material. So once this, then you do the deproduction there, and then you actually react to form the pyrazole, a proper intermediate to form the pyrazole there. Because in the molecule, we have the trifluoromethyl as well as the ester group. So you use the proper intermediate. And if you want to see if the reaction certainly works or not, we will click on the show Reaxys example, which will actually give you or show you the similar examples there. And now if you see here, the reaction similarity score is quite high because the predicted route step has closest similarity with the published synthetic route there. And due to the atom mapping, they are matching there. You see the higher reaction similarity score there. So if you can click on the Reaxys example, it will take you to again Reaxys there. So right now you might have to do multiple clicks to find out a synthetic procedure to run or execute the reaction in the lab. But once this tool gets integrated, and what Abhinav will show after my demo there, you will be able to appreciate the fact that the tool, you do not have to do so many clicks to actually arrive at. And this is an example from a patent there. And if you see, we directly provide the experimental information of the patent along with the analytical data here. So you can easily run this particular reactions at your end. So after you have achieved the pyrazole ring formation, you again do this hydrolysis of the ester and do the acid amine coupling there with the 4-amino pyridine, 4-amino 2-trifluoromethyl pyridine to form the target molecule. So this is one of the synthetic route. I'll show you one more synthetic route before I switch on to the presentation there. So if you see this particular molecule there. So this is very simple molecule, which was again in the abstract there. It starts with the 2,4,6-trichloropyridine, and you do this three steps reactions. First displacement of the 6-chloro, followed by the 4N2. But I will take you to this option, other option where we have more synthetic routes predicted by our tool there for this particular molecule. And all these 4 molecules were novel. And as you see clearly here, the tool has been able to provide you with the robust synthetic route. So again, if you see, there are 5 different routes. You see here the root confidence scores and the number of steps here clearly depicted. So as you see here, we also have the option of the lesser number of steps here. So let's go and check out that. And in the tree view, we will be able to also see which are the commercial available starting materials. So if somebody wants to see that, we have to click the tree view for to quickly check on the starting materials or the source or the building blocks. And if you see, you have the options to check on what are the starting materials. But the first step, if you see here, it's again the amide formation on the pyrazole acid chloride with the amine there to form the amide. And then once the amide is formed, the nitrile gets reacted to form the imidooxime, which actually reacts with the acid or the acid chloride as well to form the oxide azoles there, which is 1,2,4 oxide azole there. So very simple steps. And I will show from here as well now how one can get to the Reaxys examples, as I had showed earlier from the table view also. So if you can see here clearly, you have the imidooximes to react with the acid to form the oxide azoles here. And you can again click the Reaxys example actually. Again, if you see, it has very high reaction similarity score because the atom mapping was closer to the predicted reaction. The reagents are closest to the predicted reactions there. And because of that, we have the higher reaction similarity score there. And if you see here, you also have the procedure again, same as what I showed earlier. You have the link to the actual article. If you want to go and read the article, if you access to the article, you can go and check that, or you can directly execute the reaction based on the experimental data here in Reaxys itself. So That's it from the demo at this moment, but I will show you, as I told, I will switch over to the presentation and I will show you 2 more molecules, which we had. They are interesting molecule. One is the Pfizer molecule there, which was the oral drug of Pfizer for COVID-19 in the clinical trials there. So I will take you through that. So if you are able to see my slide again, and sorry to switch over a couple of times with the screen sharing there, but if you see, this is the Pfizer compound, which is in the clinical trials for SARS-CoV-2 as an oral drug there. The name is PF07321-332. And if you are able to see, this is 6-step synthesis of that particular molecules. The starting materials, again, as I showed in the earlier demos, they are commercially available. And the first step is the acid-amine coupling to form the amide, followed by the transformation of amide. So dehydration happens there. So amide to nitrile. Once you have the nitrile there, then you actually have deprotected the block. Again, if you see here, as I mentioned clearly earlier, it follows the protection-deprotection protocols, and you deprotect to form this amine there, which with another commercial starting pair or intermediate available as a building block there, it gets to do the acid-amine coupling to form the amide, followed by the block deprotection, and again acid-amine coupling to reach the molecule in 7 steps. So it's quite simple steps there to execute there for this molecule, which is recently this particular molecule was actually the structure was revealed recently in the last month itself. There is another interesting molecule from Eli Lilly, which is which actually decreases oral blood glucose there. And if you see here, this is, I think, the 7-step synthesis. Starting from if you see, they are green color boxes, so they are commercially available, and you have this reduction step to follow first. And once you have the keto reduced to the secondary alcohol there, and here you do the Sandmeyer reaction to convert the iodo to the amine. Once you have this, you couple this both, where actually this imidazole nitrogen actually gets alkylated via Mitsunobu reaction by using the secondary alcohol there to form this intermediate. Once you have this, you do with one more commercial level partner there, the Suzuki coupling, where this bromo actually gets CC bond coupling there with this counterpart boronic acid. And there is one more Suzuki coupling happening there till you reach this final molecule there. So you see, this particular tool provides you with the robust protocols, which you can quickly get the answers to your molecules and run or execute this reaction in the lab. I'm done with my part of the presentation, and Abhinav now will take you through what is next there, or what is the sneak preview in the integrated version as well. So over to you, Abhinav.
Thank you, Mandar, for that. Before I go into the sneak preview, I haven't seen anyone give us give a smile string. I don't know if everyone is aware, but to export a smile string, I'll just show you. So whatever structure you draw here, you can just click on the save button, use the drop down, and select smile. So you can just copy it and paste it in the chat along with your email address. So please provide your email address so that, in case we are unable to run the molecule during this live webinar, we can get back to you. So this is the smiles for that molecule, for the molecule that I had drawn. So draw your molecule, please hit the save button, go down, smiles, and then simply copy paste it. Copy and paste it into the chat. Right, sneak preview of what is going to come. So having proved the science, we want to work on integrating retrosynthesis into Reaxys. There are a lot of publications. So So a recent paper came out where a lot of industry partners and academics to understand how to drive adoption of AI tools in scientific community. And they defined a couple of parameters or features and functionalities that are needed to encourage the adoption of such tools by scientists. And this formed the basis of our design principles in thinking about how do we integrate the tool. So what will be released at the end of June is you will have, if you have purchased predictive retrosynthesis, it will be integrated in Reaxys. It will have an easy to use interface, and users will be able to easily edit parameters and add their custom library building blocks. So it's an intuitive and interactive interface. It does not require extensive amount of training, and people can get started very easily. So that's the first thing that we, as we learned from our design principle, that it should be easy and intuitive. So we try to meet that. The second thing is, when you do the search in Reaxys, when it is integrated in Reaxys, it will give you predicted route and published route all in one place. So if a molecule is known, you will get the published route as well as the predicted route in one view. So you do not have to run two searches. You will have commercially available, you can place an order for commercially available starting materials right from this view. It will also give you the number of steps required in the route. And what it will also give you is an interactive and graphic route overview to assess linearity or branching of the route, to assess complexity, to compare these multiple routes together. It provides you with a scoring system for ranking the routes. And when you click on table or tree view, in tree view, what you see is you have an easy navigation panel so that you do not have to switch between multiple windows or go back and forth. You have all the data that you need visible in one window. So the route itself, for every step, the literature precedents that inform that step, and experimental procedure, yield if it is provided, and literature reference. Same for predicted one, you have the literature precedents of the published route that inform the predicted route is visible in one view, so that you can, you don't have to click back and forth. And you have all the data, all the information that as a scientist that you need to make a decision whether this particular step or any of these particular route is a scientifically robust and viable route proposition for you to take to the lab and execute the synthesis. Further to this, the export functionality will be available. Right now, as Mandar was showing, you have export functionality covering only PDF, but once it is integrated in Reaxys, it can be exported in multiple different formats that you may be familiar with, and you can use it directly to add to your ELNs. Hopefully, I have been able to illustrate that you require 3 key ingredients for making such AI tools to be used successfully by scientists. You obviously need top-notch data science. So the 3 neural network coupled with Monte Carlo tree search that Mark has developed. You combine that with really high quality data because artificial intelligence without data is just artificial. And then you deliver the whole package in an excellent, easy to use, intuitive user interface to deliver an excellent user experience. And that is what will help drive adoption of such tools by scientists, and it will help augment the your work. So, Jürgen, do you want to take over for the summary and outlook?
I think it's just 2 slides, so maybe you should just continue with it, right?
Yeah.
Okay, cool.
So,
good.
In summary, I hope we have been able to show you that, one, it is, retrosynthesis tool is a great idea generator. I want to be very transparent and honest that, it will not replace chemists. It will augment the knowledge of chemists. It will give you ideas on how to go about your day-to-day work. It is definitely very fast. So you can run multiple searches, multiple strategies at the same time. It takes into account all published knowledge from patents and journals. So as human beings, we can only keep limited things in mind, but having such a tool, it takes into account all of the chemistry that is published. It provides scientifically robust suggestions, mostly because, some synthesis, it's challenging. Some synthesis are challenging for human beings. And similarly, some synthesis are super challenging for any AI system as well. If you use really complex multi-cyclic ring systems or have natural products, then that is going to be a challenge both for human beings who are experts with lots of years of experience, as well as for AI systems. And every root proposition, every step that is predicted is linked to a published literature, so that it's not a black box. You can see and make a informed decision and informed judgment about whether that chemistry being proposed is going to, you think that is robust or not. So it is great. So what's next? In the field of predictive retrosynthesis, there are some general challenges that everyone is dealing with. Stereochemistry, we hear this quite often, but can it handle stereochemistry? So at the moment, it cannot. None of the tools can. And we need more data on stereo-specific reactions and better descriptors. Excuse me. Complex natural products, there are not many full synthesis routes published, so it definitely requires more data. Regio and chemoselectivity, it does respect regio and chemoselectivity to a certain extent, but definitely it can be improved, and algorithmic approaches need to be further developed to improve this. We often hear about breaking complex ring systems. Sometimes you will see, sometimes when you try it, you will see that it is unable to break complex ring systems. So in a recent paper by Amol Thakur from Bern and AstraZeneca, they have proposed an interesting approach. We are looking into it. Inorganic molecules are currently not handled at all. So what are we working on for the rest of the year and next year? We want to have a feature for the user to be able to define the bond to break or the bond to protect. So that is one of the features that we have heard quite a lot about, that users have requested. So we are working on introducing that feature. We also know that sometimes users would like to define what intermediate to include or exclude. So if you have certain toxic intermediates that you would like to exclude, or if you want the retrosynthesis to go through a particular intermediate, we've heard this requirement from users as well. So definitely working on those. more flexibility in editing, so in selecting, modifying, so that you can work in a group together, further improving regio and chemoselectivity. For computational scientists, user interface is good, but they also need API support. So we're working on having a retrosynthesis API. Further increase the diversity of the root proposition so that it gives you multiple ideas, and to integrate commercial substance, Reaxys commercial substances database rather than Sigma Aldrich lab networks. Commercial substances are, to define those commercial substances or building blocks are important because they act as top criteria. In the Reaxys commercial, we have approximately 50 million, 60 million commercial substances. So integrating that into retrosynthesis will definitely further enhance the performance of predictive retrosynthesis. With that, I would like to thank you all for your attention, and we are all happy to answer any questions you may have. If you have any smile strings, either now or after the webinar, please, I think Maria and Lillian have provided their email address.
Yes.
So feel free to email it to us.
We have a nice question for Ariadna Garza. Hello, Ariadna. I believe you are one of our LATAM advisors. And she is a professor of organic chemistry in Mexico, if I'm not wrong. So she is telling to us, I was wondering if the commercially synthetical procedures are considered in the database. Due to the difference in scale, the proposals could be impossible to perform in small scales. The analysis have a way of discriminating such problems for the retrosynthetical proposal?
Well, let me take that. So typically those reactions are in Reaxys and on various scales, I have to say. But the tool right now doesn't take conditions or yields or scales into account. So the reaction type itself is in the tool if there is enough precedence from the public literature, but we don't discriminate by the scale or the yield of the products.
Yeah, she's just adding that, yes, here I'm trying to learn a bit more. What is the main problem when using the retrosynthetical tool? Some advice for the people starting the use?
Yeah, I guess you have the right people on the call to answer that question, because we have used it so intensively so far. And I think the biggest thing that you need to keep in mind is that RT, as it is right now, is not the answer to everything, right? But you should not, let's say, lose focus or let's say stop if the tool tells you no results, right? It's actually the beginning of a journey. And as Mandar was showing, you can do other options. You can prolong the processing time. You can play with the last step only option, or you can also play a little bit with the building blocks. And you can also use your own intuition and say, I start with a slightly different and modified molecule and see whether that works. The good thing is it is fast, right? So you don't need to wait a day before you get an answer. So normally the typical processing time is 10 minutes. So in 10 minutes, you can play around with it quite frequently. Abhinav, Mandar, anything to add?
No, perfect, yeah.
There is, as Jürgen was saying, the only thing to add is sometimes as human beings, we have aversion to AI. And as experts in the field, especially with so many years of experience, it's only natural response that comes to our mind that, oh, for sure a machine can't do what I can do as an expert. And there was a very interesting publication where, aversion to algorithms. And what this shows is that, despite algorithms being sometimes more correct, whenever it makes a mistake, people, and just human beings in general, think more negatively of algorithms than they would think of human beings making a mistake. They are less forgiving on algorithms, which is fair, which is, it will require us to adapt our behavior, and it is going to be a slow process. But we just need to manage our expectations, as Jürgen said. We cannot take that, okay, whatever route it proposes, I'm just gonna, or if it doesn't propose a route, I'm gonna lose my faith in it. But there are ways to utilize this tool to augment our knowledge. The key thing is to remember that such tools are there to really support you and to augment your existing expertise and knowledge, not to follow them blindly and not to replace any experts. And for starting to use, I think, yeah, you just have to, we are always interested, like we're working with some of the laboratories on them using the tool and actually going to the lab to see whether those molecules, like for example, the molecules that Mandar was showing, they are novel molecules, and to take those procedures to the lab and actually try it in the lab, because that's the ultimate test.
Yes, that's true. Could be.
Yes and no, because the way some of the academics are using such a tool is quite interesting. It is like, a good analogy is chess. When IBM's, the Deep Blue computer came out, which played against Garry Kasparov, everyone thought that, oh, now human chess players might become, where do we go? But actually what happened is that, expert human chess players now routinely play against machines to train themselves to become even better. So actually two of the academic groups, what they are using predictive retrosynthesis for teaching is that in a student project, they give student or a group of students a molecule and ask them that, hey, why don't you come with develop a synthetic procedure for this molecule? And then in a group setting, they say that, okay, now use predictive retrosynthesis to come up with a route. See what route does AI predict for this molecule. And as a scientist, as a group, they do an exercise where they compare the route that they came with to the route proposed by predictive retrosynthesis. Because that's how you learn, at least that's how we learned synthesis. That, oh, here I did, as Manda was showing, here I did acid-amine coupling, but retrosynthesis, like the AI tools, in fact, started with doing a Bock deprotection, maybe, or a Mitsunobu reaction. Maybe I did not think of that strategy in my mind. So that way, I know of two really leading academic institutions who are using predictive retrosynthesis for teaching. It's definitely not for first-year students, I would say, but when they learn a little bit more about synthesis, then it is a very good tool to really learn to synthesis, to think about different approaches for solving a synthetic challenge.
Yes, we have another question in the Q&A from Marco Espinosa. Good morning. Will this method always obtain the highest possible yield?
No, actually it is completely yield agnostic. So as I said, it doesn't take conditions or yields into account. Rather, what it does is it creates templates from the Reaxys knowledge base, and templates are created if a given reaction has been mentioned at minimum 3 times in Reaxys, right? And that is then a rule for the tool to proceed further.
Okay. So before we finish, as considering we don't have any more questions, I just want to raise a poll. If you guys could please answer this poll. How likely are you to recommend this session to a colleague? So if you could just answer and send back to us, please.
I can answer that as well.
Speakers can answer these as well. So this session is recorded. It's going to be available in our YouTube channel, as I think this afternoon, or you can also ask for us on demand. We plan a second session in July or August by the time this tool is already integrated into Reaxys. So stay tuned in our social media channels or even contacting us, me and Maho that is here. There is a few to answer, so I'm just waiting for a couple of minutes, and taking advantage also to thank you very much for this opportunity. Thank you all of the speakers, Jürgen, Mander, and Abhinav, for this extremely wonderful presentation to us. And I'm also going to end the poll now. Yeah. Let me share the results. Extremely likely to recommend. So it's the highest percentage here. So I don't know if you want to make any comment, feel free.
Well, I mean, if you would like to have this presentation or deeper dive at your institution, please contact Lillian. I'm sure she will be able to arrange a deeper dive presentation, and you can send her the molecules of your interest to run in retrosynthesis, so that the presentation that is delivered to your institution or to your research group becomes more relevant.
Yes, thank you. Anyone else wants to have final words?
I also would like to thank the audience for joining the call, and hopefully you found it interesting, and that's what the poll actually proved, of course, and looking forward to a bright future of retrosynthesis in Reaxys, and also for you to use it and comment on it so that we can develop it with your feedback moving forwards. Thank you very much.
Thank you, Jürgen. Okay, so I will stop recording. Thank you very much. Have a nice day. Bye-bye.
Bye-bye.
Bye.